Introduction. In modern era, we cannot think about life without electricity. Each and every moment we need electricity directly or indirectly. In this chapter, you are going to learn about the technical aspect of electricity. You will be able to deal with various laws, components and connections. We will also learn about the heating effect of electric current.
We will be discussing following points in this chapter: electric current and circuit, electric potential and potential difference, circuit diagram, Ohm's law, resistance of a system of resistors, resistors in series and parallel, heating effect of electric current, practical applications of heating effect of electric current, electric power.
Electric current and circuit. Basics. Something which is flowing or having motion is called current. You are familiar with water current and wind current. Similarly, when electrons move in an electric conductor, it is said to be electric current. Do you know? Electron is not invented when the phenomenon of electricity invented. So electric current considered to be flow of positive charge. Conventionally, the direction of current is taken as opposite to direction of flow of electron, which is known as conventional current. Motion of electron is only possible when it finds a closed path. A continuous and closed path of electric current through a conductor is known as electric circuit. Electric current is defined as the amount of charge flowing through a particular area in unit time. That is, rate of flow of electric charge. If Q is net charge, T is the total time of charge flow, then current I is given by I is equal to Q divided by T. SI unit of charge is Coulomb, that is C. That is charge of nearly 6 multiplied by 10 to the power 8 electrons. Charge of a single electron is 1.6 multiplied by 10 to the power minus 19 Coulomb. Unit of current is ampere, that is A, named after French scientist André-Marie Ampère, 1775 to 1836. When 1 Coulomb of charge flow for 1 second, it is said to be 1 ampere current. An instrument which measures current is called ammeter.
The schematic diagram of a typical electric circuit comprises a cell, an electric bulb, an ammeter and a plug key. The electric current flows in the circuit from the positive terminal of the cell to the negative terminal of the cell through the bulb and ammeter.
Electric potential and potential difference. Concept of electric potential. Consider the flow of water. It always flows from higher level to lower level because of gravity. It never flows on same level. Same thing happens in the case of electric current. It always flows from higher charge level to lower charge level. The charge level is known as potential. It means electricity flows from higher potential to lower potential. Analogous to the property of water, it never flows between same charge levels or when the potential difference is zero. The potential difference between two terminals is made by using a battery. Scientifically, electric potential difference is the work done to move a unit charge from one point to other. Potential difference V is equal to work done, that is W, divided by charge, that is Q, or V is equal to W by Q. The SI unit of electric potential difference is volt, named after an Italian physicist Alessandro Volta, 1745 to 1827. Volt is the potential difference between 2 points of a conductor when 1 joule of work is done to move a charge of 1 Coulomb from one point to another. Mathematically, 1V is equal to 1J divided by 1C. The device which is used to measure the potential difference between 2 points is called voltmeter. Various symbols of electric components. Ohm's law. Very fundamental law of electricity. To know the relationship between potential difference and current through a conductor, let us perform an activity. Take 4 batteries, 1.5 volt each, an ammeter, a voltmeter, a plug switch, and nichrome wire of XY length. Connect all these components as shown here. Make a table as shown below and note down ammeter reading and voltmeter reading. Also calculate the respective V upon I each time by increasing the number of battery in the circuit. Voltage across A, 0. Current through V, 0. Voltage across, that is A, 2. Current through, 0.5. A, 4. V, 1. A6, V1.5, A8, V2, A10, V2.5, A12, V3. Draw a graph between V and I. What do you observe? The VI graph is a straight line passing through origin, indicating a linear relation between V and I. You can easily notice from Ohm's law that current can be controlled using resistance. If we increase resistance, then current decreases. In 1827, George Simon Ohm, a German physicist, finds a linear relationship between V and I. He stated that the electric current flowing through a metallic wire is directly proportional to the potential difference V across it, provided its temperature remains constant. This is called Ohm's law, that is, V directly proportional to I, or V divided by I is equals to constant, that is equal to R, or V is equal to IR. This is equation 1. Where R is called resistance of given metallic wire, which is a constant and different for different metal at constant temperature. SI unit of resistance is Ohm. From equation 1, R is equal to V upon I. In a circuit, a device called rheostat is often used to change the resistance. Factors affecting resistance. Resistance in a conductor depends on nature, length, and area of cross-section of the conductor. Number 1. Nature of material. Some materials create least hindrance and hence are called good conductors. Silver is the best conductor of electricity, while some other materials create more hindrance in the flow of electric current, that is, flow of electrons through them. Such materials are called bad conductors. Bad conductors are also known as insulators. Hard plastic is one of the best insulators of electricity. Number 2. Length of conductor. Resistance R is directly proportional to the length of the conductor. This means resistance increases with increase in length of the conductor. This is the cause that long electric wires create more resistance to the electric current. Thus, resistance R is directly proportional to length of the conductor L, or R directly proportional to L, equation number 1. Number 3. Area of cross-section. Resistance R is inversely proportional to the area of cross-section A of the conductor. This means R will decrease with increase in the area of conductor and vice versa. More area of conductor facilitates the flow of electric current through more area and thus decreases the resistance. This is the cause that thick copper wire creates less resistance to the electric current. Thus, resistance R is directly proportional to 1 upon area of cross-section of conductor A, or R is directly proportional to 1 by A. This is equation 2. From equation 1 and 2 we get R directly proportional to L by A. That is equal to R is equal to rho multiplied by L upon A. This is our equation number 3. Where rho is the proportionality constant, it is called the electrical resistivity specific resistance of the material of conductors. From equation 3, Ra is equal to rho multiplied by L. This gives rho is equal to R multiplied by A divided by L. The SI unit of resistivity. Since the SI unit of R is ohm, SI unit of area is meter square and SI unit of length is meter. Therefore, unit of resistivity rho is equal to ohm multiplied by meter square divided by m. This gives ohm meter. Thus, SI unit of resistivity is ohm meter. Materials having resistivity in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter are considered as very good conductors. Silver has resistivity equal to 1.60 multiplied by 10 to the power minus 8 ohm meter, and copper has resistivity equal to 1.62 multiplied by 10 to the power minus 8 ohm meter. Rubber and glass are very good insulators. They have resistivity in the order of 10 to the power 12 ohm meter to 10 to the power 17 ohm meter. Resistivity of materials varies with temperature. Resistance. In a circuit, some materials allow flow of larger current through them than others. In other words, certain materials offer more resistance to flow of current than others. The property by virtue of which a material opposes or limits the flow of electric current through it is called its electric resistance. Electrical resistance is the property of the electrical element to oppose the flow of the current passing through it when a voltage is applied across the element. It is mathematically represented as the ratio of the voltage to current. R is equal to V divided by I, where R is equal to resistance. V is equal to voltage across the electrical element. I is equal to current flowing through the electrical element. The electrical resistance is measured in ohm. The unit is named after German physicist George Simon Ohm, who discovered the famous Ohm's law. Ohm is the SI unit of resistance. The Greek letter omega is used to represent resistance. Definition of ohm. 1 ohm is the resistance of a conductor through which a current of 1 ampere flows when the potential difference across its ends is 1 volt. Component that is used to resist the flow of electric current in a circuit is called resistor. In practical applications, resistors are used to increase or decrease the electric current. Variable resistance. The component of an electric circuit which is used to regulate the current without changing the voltage from the source is called variable resistance. Rheostat. This is a device which is used in a circuit to provide variable resistance. Conductors. Rate of flow of electrons in a conductor is electric current. The particles of conductor create hindrance to flow of electrons because of attraction between them. This hindrance or resistivity is the cause of resistance in the flow of electricity. The resistivity is the opposition strength of the electrical elements. Number 1. Substances which allow electricity to pass through them easily are called conductors. These are made from materials which have low resistances. Metals like copper, aluminium, silver, iron, brass, and also salt solutions are good conductors of electricity. Number 2. Insulators. Substances which do not allow electricity to pass through them easily are called insulators. These are made from materials which have a higher resistance. Some substances like air, plastic, cotton, rubber, wood, paper, glass, pure water, etc. are insulators. Resistors in series. When two or more resistors are connected end-to-end consecutively, so that the same current flows through all of them, then the resistors are said to be in series. A series circuit has one path for the electricity to travel through. In series combination of resistors, the current is the same in every part of the circuit, or the same current throughout the circuit. Law of combination of resistors in series. If two resistors R1 and R2 connected in series, a battery of V volts is applied to the end of this series combination. Let the potential difference across R1 as V1 and that across R2 as V2, since V represents energy. According to the law of conservation of energy, V is equal to V1 plus V2. This is equation 1. That is, the total potential difference across the two resistors should be equal to voltage of battery. Using Ohm's law, V is equal to IR. This is equation number 1. V1 is equal to IR1 and V2 is equal to IR2. This is equation 2. When I is the current flowing through the circuit and R represents the equivalent resistance of the two resistances. Substituting 2 in 1, we get IR is equal to IR1 plus IR2. That gives R is equal to R1 plus R2. The equivalent resistance is the sum of the individual resistances connected in series. The above result can be generalized for n number of resistances of different values as R is equal to R1 plus R2 plus Rn. Resistors in parallel. When two or more resistors are in such a way that the potential difference across them remains the same, they are said to be connected in parallel. When resistors are joined in parallel, the reciprocal of total resistance of the system is equal to the sum of reciprocal of the resistance of resistors. That is, sum of the reciprocals of all the individual resistances. Law of combination of resistors in parallel. If two resistors R1 and R2 are connected in parallel to one another between the points A and B, connect this combination to a battery of potential V. Here the potential difference across R1 and R2 will be equal to battery voltage, but the total current I flowing in the circuit branches as I1 through R1 and I2 through R2. Since there cannot be accumulation of charges at any point, I is equal to I1 plus I2. This is equation 1. Using Ohm's law, I is equal to V upon R, I1 is equal to V upon R1, I2 is equal to V upon R2. This is equation 2. Substituting the values of equation 2 in equation 1, we get V upon R is equal to V upon R1 plus V upon R2, that is equal to V in bracket 1 upon R1 plus 1 upon R2. This is equation 3. On dividing equation 3 throughout by V, we get 1 upon R is equal to 1 upon R1 plus 1 upon R2. If the resistors are connected in parallel, the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of all the individual resistances. This result can be generalized for any n resistors. Therefore, 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus 1 upon Rn. Disadvantages of series connection and advantages of parallel connection. Disadvantages of series of combination. Current is constant throughout the electric circuit. Example, if we connect a bulb and a micro-oven in a series, it is impracticable because both of them need different values of current. If one component in series fails, the circuit breaks and none of the components work. Example: fairy lights. Lights used for decoration. All electrical appliances have only one switch, due to which they cannot be turned on or off separately. The appliances do not get same voltage as that of the power supply line. The overall resistance of the circuit increases too much, due to which the current from the power supply is low. Advantages of parallel. If one electrical appliance stops working due to some defect, then all other appliances keep working normally. Each electrical appliance has its own switch, due to which it can be turned on or off independently, without affecting other appliances. Each electrical appliance gets same voltage as that of the power supply line. The overall resistance of the household circuit is reduced, due to which the current from power supply is high.
We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. We have also seen that to maintain the current, the source has to keep expanding its energy. Where does this energy go? A part of the source energy in maintaining the current may be consumed into useful work, rest of the source energy may be expended in heat to raise the temperature of gadget. We often observe this in our everyday life. For example, an electric fan becomes warm if used continuously for longer time etc. On the other hand, if the electric circuit is purely resistive, that is, a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron etc. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time T. Hence the power input to the circuit by the sources or the energy supplied to the circuit by the source in time T is P into T, that is V, IT. What happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus for a steady current I, the amount of heat H produced in time T is applying Ohm's law, we get H equals I2, RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is I directly proportional to the square of current for a given resistance. E directly proportional to resistance for a given current, and E directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a known voltage source, is used after calculating the current through it, using the relation I is equal to V upon R. Practical applications of heating effect of electric current. The generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful electrical energy into heat. In electric circuits, the unavoidable heating can increase the temperature of the components and alter their properties. However, heating effect of electric current has many useful applications. The electric laundry iron, electric toaster, electric oven, electric kettle and electric heater are some of the familiar devices based on Joule's heating. The electric heating is also used to produce light, as in an electric bulb. Here, the filament must retain as much of the heat generated as is possible, so that it gets very hot and emits light. It must not melt at such high temperature. A strong metal with high melting point such as tungsten melting point 3380 degrees Celsius is used for making bulb filaments. The filament should be thermally isolated as much as possible, using insulating support, etc. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of filament. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. Another common application of Joule's heating is the fuse used in electric circuits. It protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with the device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point, for example aluminium, copper, iron, lead etc. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1, 2, 3, 5, 10 ampere, etc. For an electric iron which consumes 1 kilowatt electric power when operated at 220 volt, a current of 1220 ampere, that is, 4.54 ampere will flow in the circuit. Fuse of 5 ampere must be used. Electric power. You have studied in your earlier class that the rate of doing work is power. This is also the rate of consumption of energy. This gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by the following formula. The SI unit of electric power is watt W. It is the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. Thus, 1 watt is equal to 1 volt into 1 ampere. The unit watt is very small. Therefore, in actual practice we use a much larger unit called kilowatt. It is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electric energy is, therefore, watt-hour (Wh). 1 watt-hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt-hour (kWh), commonly known as unit.